Hey everyone, welcome back to physics. This will be lecture 12 of the course, and in this section we're going to start our third chapter of our grand physics class here, and that chapter is going to be concerned with Newton's laws of motion. So up until now we have talked about kinematics, both 1, 2-dimensional and 3-dimensional kinematics, n-dimensional kinematics, and we haven't really been concerned about the sources of motion. We've only been concerned about solving motion problems, understanding motion problems from the standpoint of kinematics. But now what we want to do is we want to start to introduce some of the sources of motion. And so naturally we'll have to begin with the concept of a force, and Newton's laws of motion are all about forces and how they interact and cause motion. So let's go ahead and get started. So we'll call this section 3.1, force and interaction. And so this section here is going to be probably a little bit lengthier and probably a little more conversational. Here we'll be focused on identifying what a force is, as well as going through several key examples of forces that we'll come across in our example problems, and just fundamental sort of forces that operate in the world. And so let's start with, what do we mean by a force? We'll say that a force is a mathematical push or pull. It's a mathematical push or pull, and specifically a force is a mathematical push or pull that causes a body to accelerate. All right, and we should be careful here. It causes a body to accelerate unless, as we will see, there is a counterforce to offset it. To offset it. Okay, so a force is a mathematical push or pull. And specifically, our interest in forces is that it causes a body to accelerate, i.e. it creates motion. So all motion begins in acceleration, and forces are what cause bodies to accelerate. And so we can kind of, right off the bat, distinguish between two types of forces. The first type is what would be called a contact force. Contact force. Contact force is any force that involves direct contact between two bodies. So any force that involves direct contact between two bodies. Okay, so these are the kinds of forces, if I get hit by a car, the force that is impacted into my body is a contact force indeed that comes from the car. These are, another example would be like a hand just pushing a cart, a tire on a car interacting with the road, so there's a push, there's a contact force there. Another example would be like a locomotive or a train that's got a bunch of cars hooked up to it. It's pulling the car, so that's a contact force. So we're very familiar with this type of force. It's all around us in the world. Now another type of force, which I would say is just as common, but maybe they're forces that we are somewhat less aware of, although if we think about it, they're not hard to become aware of, and those are long-range forces. So long-range forces. Right, and so these are forces that act between bodies that are not in direct contact. Forces that act between bodies that are not in direct contact. Okay, so forces that operate between bodies still, all forces have to be between bodies. If you don't have multiple bodies, you don't have a force. But in this case, the bodies do not have to interact. They don't have to actually, well, they interact. They don't have to touch. They don't have to be in direct contact. So a good example here would be like magnets. We've all had experiences with magnets. We take two magnets and we take the positive ends of magnets and we bring them close to one another. They push away, right? You can feel a force of the magnets repelling one another, right? Even though they're not in contact. And similarly, if you flip them around, you have a positive and a negative side, you pull them close to each other, they attract, right? So if I have a positive and a positive magnet, then they kind of push against each other, right? Whereas if I have a positive and a negative, they tend to want to pull together. They'll snap together, right? The force begins well before they're in contact. That's the key. They're long-range forces. Another example that's the obvious example would be gravitation, right? So gravity pulls on objects that are near the Earth specifically. I mean, we think about the gravity of the Earth, but any body actually has gravitation, right? So, but if we jump out our second-story window and we fall, why do we fall? Well, we fall because of gravitation, because of a long-range force that the Earth exerts on us, and also we exert on the Earth. Okay, so these are two very clear examples of the idea of a long-range force. Now, gravitational attraction, the name of that force is actually weight. Like we are all very familiar with the concept of how much we weigh, but that weight is actually your mass times the force of gravity, right? So that technically that is a force. Your weight is a force. All right, and we'll get into gravity in just a moment, actually, but that'll be our first foray into the major forces. Now, mathematically, we think of forces as vectors. So forces are vectors. And why are they vectors? Well, they're vectors because they have both magnitude and direction. They have both magnitude and direction. Of course, that's what we mean by a vector. This is obvious, right? If I fire a gun, the bullet is going to have a magnitude, obviously, the speed of the thing, but it's also going to have a direction, a very specific direction, right? And so to properly model that, we have to think of it as a vector. Okay. Now, we'll get into this in a minute, but at any given time, lots of different forces can be acting on a particular body. So if I've got force 1 and force 2, force 3 and force 4, all of these forces are interacting on this body at the same time. They're operating on the body in different directions, and so modeling these things with vectors is absolutely it just doesn't make sense to model it any other way. Now, when we talk about a force, we quantify them using what are called newtons. So we quantify forces using units called newtons, right? And it turns out that a newton, 1 newton equals 1 kilogram meter per second squared. So you can already kind of see that you've got a mass involved here, i.e. the kilogram, and you've got a meter per second squared. We tend to think of as an acceleration, and so when we get into Newton's laws, Newton's second law in particular, you'll see exactly where these units come from. So obviously these units are named after Isaac Newton, who was the first, he was the natural philosopher who first laid down a sort of complete at the time explanation of forces in motion. It really created the first idea of how forces work and how they generate motion. Okay, so we want to start by briefly introducing Newton's 3 laws of motion, because they're helpful in helping us to understand what a force is, and we also will reference them as we look into some of the common forces from our everyday experience. Now, all of these we will give a more thorough treatment of in the coming lectures. This is really just to kind of get them out there so that we can derive a better conception of what a force is, and also so we can reference them as needed. All right, so we'll start with Newton's first law. Newton's first law. Okay, and so all of these I think people are likely to be familiar with. Actually, I mean, the first and the third are almost like so deeply ingrained in our cultural understanding that they almost like rise to the level of like nursery rhymes. Like you hear them and you're like, oh yes, I know that, I've heard that, even if you're not a scientist or someone with much interest in science. The second one is slightly less well known probably to the general lay audience, but Newton's first law says that objects in motion, I'll write it out in its complete form, objects in motion tend to remain in motion unless acted upon by an outside force. Objects in motion tend to remain in motion unless acted upon by an outside force, right? And it also says that objects at rest tend to remain at rest unless acted upon by an outside force. So objects at rest tend to remain at rest unless acted upon by an outside force. Okay, so this is kind of the common language that's used to describe Newton's first law. This isn't the exact phrasing that he used. It's also not the exact phrasing that like we will use in our next lecture specifically on Newton's first law. But this is the language that people are probably familiar with. Objects in motion / rest tend to remain in motion / rest unless acted upon by an outside force. So there's a lot to break down in here, but basically the idea with Newton's first law is that objects have this property called inertia. They want to stay put or they want to keep moving, right? And it requires a force, an outside force, as the phrasing goes, to cause them to change. They don't change all of their own accord. They don't start moving all on their own. They require some kind of a push or pull. And they don't stop moving on their own or change direction on their own. They also require a push or pull for that. Okay, so this kind of goes back to our original notion of a force as a push or pull that causes motion unless it's balanced by offsetting forces, right? So this idea of an outside force, I mean, the schematic I've drawn up here, it's very possible that this could be an object at rest. You've got these forces interacting, and maybe they're offsetting each other just precisely. But if another force comes in, an outside, quote-unquote, outside force, then you could start to see motion, right? So outside force is a little bit vague, but that's okay. We'll get to something more precise later on. The key with Newton's first law is just to recognize that that objects want to stay put unless something comes along and pushes them, and they don't want to be halted, and it requires some kind of outside effort to halt them. So that's Newton's first law. And again, we'll come back to this with more rigor later on. Newton's second law then, Newton's second law can be, let's see, so Newton's second law. Newton's second law can be stated as forces accelerate objects according to, and so frequently you'll just see people write F equals ma. All right, but actually, given the fact that there can be many forces involved, we say the sum of the forces is equal to the mass times the acceleration. So force is equal to mass, the product of a mass and its acceleration. Now again, we think of forces as vectors, and we also think of acceleration as a vector. So mass is a scalar that gets tossed onto the side of this acceleration vector. Okay, now what are all these things here? Well, we've already discussed the force is a mathematical pushes or pulls. Okay. And we say that there's a sum, right, because different forces may be acting at the same time. So different forces may be acting at the same time. Okay. So I've got different mathematical pushes or pulls acting at the same time. We add them all up, and that gets me the left-hand side of the equation. What's on the right-hand side? Well, this is just acceleration. So acceleration is caused by forces. Okay, and we know the units there is meters per second squared. And then this m, we haven't really talked much about mass yet, but this is mass, which is you can think of it as a quantity of matter, stuff, otherwise known as. So you've got a mass here, which is a quantity of matter. Now, mass also, I mean, you can think of it as how much stuff is in an object, right? So we all have an intuitive sense of things that are more or less massive. Things like a hollow glass orb has far less mass than a solid steel orb of the same diameter, right? So clearly, we have an intuitive sense of this. From the standpoint of physics, we think of mass as, at least initially, as a quantity of matter. Now, another thing is that because it's a scalar on this acceleration vector, mass also describes how an object resists motion. So it also describes how an object resists motion. This is back to the idea of inertia. We'll get into inertia in a lot of detail later, but if something's super massive, it takes a lot of force to slow it down. Conversely, if something is very lightweight and has no mass or minimal mass, then it's very easy to stop it. You just stick your finger out and you can poke it and stop it, right? Where you can't do that, like a semi-truck versus a feather, right? Big difference, right, in terms of their inertia. And that's directly related to how much mass they have. Okay, and so on the left-hand side, you have the sum of the forces. On the right-hand side, you have mass times acceleration. Mass is measured in kilograms. And so here we get the idea of a Newton. A Newton, denoted just N, is equal to kilogram meters per second squared. Okay, so that's Newton's second law. It gives us a mathematical relationship between forces and mass and acceleration. So that's the second law of Newton, and everybody will have heard of the first law for sure, not for sure, but most likely, and the second law is the most obscure of the three. Now the third law, I would say, is probably Newton's most well-known, and this one is almost poetic. Newton's third law. What does Newton's third law say? Newton's third law says that for every force, there is an equal and opposite force. I think actually the way phrased by Newton, it's probably more like for every action. For every action, there is an equal and opposite reaction. I think people will be familiar with it using that wording. But by action, we mean force, and of course reaction, we just mean opposite force. And so a couple of things to note here. First of all, forces only exist when you have multiple objects. An object can't have a force an object can't exert a force on itself. It can only exert a force on another object, and it can only have a force exerted on it by another object, right? So forces are interactions between objects. So a couple things to know here. Forces are interactions between objects, right? Always. Okay. And another concept here is that an object feels the same force magnitude as the thing exerting the force, right? So, like, for example, if I, imagine you have a wagon, and this is going to be intuitive. People will be able to relate to this immediately as soon as I say it. If I've got a wagon and it's like a hand cart, right, and I pull on it, there's a pull. All right, I pull on the wagon. Then what we say is that the wagon pulls on me. Or I can feel it in my arm. When I pull on something, I feel my arm being pulled on. Right? And so that's this Newton's third law sort of in reality. This is how you're familiar with it. Right? When I pull on something, I feel it pull back on me. Just like if I push down hard on the desk in front of me with my hand, I feel it in my hand, and that's really the desk pushing back against me. Okay. Another example that you're going to be very familiar with is when you stand up, you feel the earth exert a force on you, right? It pulls you down, right? But in reality, this is, and this may not be something you consciously think about, but you also exert a force on the earth, right? It's just that the earth is so much more massive than you, it's inconsequential, right? But certainly the earth's force that's being exerted on me is not inconsequential. So Newton's third law basically says that forces are interact with one another. When I exert a force on an object, it exerts a force back on me. Okay, and that these forces are equal and opposite. Okay, very good. Let's next talk about some of the common forces. So let's get into the forces that we'll need at least for chapter 3, and we'll get into some more later, and some of them we'll get into much more detail later. But some of the common forces are what we want to lay out next, and we'll start with gravity. All right, so gravity. Gravity is the force of attraction between bodies. This is a force of attraction between bodies. Okay, so obviously the force is most apparent between the Earth and objects near the surface of the Earth, but it's not true that only the Earth has gravity. All objects exhibit gravity. It just happens to be quite weak unless the body in question is very massive, such as the Earth. Right? So the Earth has gravitation that holds us to it. Right? So this is the one you're most familiar with. A lot of times when people say gravity, you really just think like, oh, the Earth has gravity. It's actually a property of all matter. All objects have gravity. It just happens to be a pretty weak force, and it only becomes significant when the body is humongous. Okay, and so let's kind of jump into gravitation just a little bit and think about it. I want to do kind of a thought experiment. Right, as we kind of talk this through. Imagine that we have two balls. Imagine we have two balls, right? And so we'll say that they're the same size, meaning they have the same diameter. All right, so you've got two of them. One of them is going to be steel, and the other is made of wood, right? And so the different materials means they're going to have different mass. And so we'll say the steel ball is 2 kilograms and the wooden ball is 0.5 kilograms. Now, it can be shown by experiment that these two objects, even though they have very distinct masses, they fall at the same rate, assuming no air resistance. So these two fall at the same rate, right? Certainly if you put them in a vacuum, you have like a controlled experimental apparatus that's like a vacuum, and you do this, you will see that they fall at exactly the same rate. But even in normal atmosphere, this would, over not too big of a distance, these would fall at roughly the same rate. You wouldn't be able to probably detect it with your eyes. All right, so let's break this down a little bit. So the steel ball has a mass of 2 kilograms. Let's think about the force of gravity operating on the steel ball. So we'll just denote it as F of S. And it turns out that the force of gravity is the force caused by gravity can be thought of as m times g, where g is the gravitational force. And so this would be equal to 2 kilograms. In this case, it would be 2 kilograms times 9.8 meters per second squared. Right, so actually the g here is not a force, it's the acceleration due to gravity near the surface of the Earth. Right, and so for a 2 kilogram steel ball, the force exerted on it by the Earth would be about 19.6 newtons when you multiply this together. Now, on the other side, you've got the wood, right, the wooden ball, and it's also going to be equal to the mass of the thing times the acceleration due to gravity. And when we kind of multiply that out, we get 0.5 kilograms times, again, 9.8 meters per second squared. And so we see in the case of the wooden ball about 4.9 newtons of force. Okay, so the force of gravity is different on these two objects, right? And we start from the standpoint that we know what's going to happen, mass times acceleration. If we drop these, the mass is what it is. The acceleration we know will be 9.8 meters per second squared, so we can identify the force. So the force of gravity is different on these two objects. The force felt by each ball is the ball's weight. So the force felt by each ball is the ball's weight. Okay, and it's different. Right? So in particular, the force that's being applied to the steel ball is a larger force. Right? So it's a little bit difficult to understand how, if a larger force is being applied to the steel ball, why doesn't it fall faster? Shouldn't it fall faster? Right? If a larger force is being applied to the steel ball, shouldn't it fall faster? Right? It feels like that's how it should be, but it actually isn't, right? Right? And the reason it doesn't fall faster is it has a larger mass. The steel ball has a larger mass. Okay, it has a larger mass. And again, remember what we talked about earlier. We talked about mass in some respects being thought of as a body's resistance to acceleration. Right? So in order to accelerate the steel ball at the appropriate rate, 9.8 meters per second squared, a larger force is required. Right? The wooden ball is less resistant to acceleration than the steel ball, right? This is a way of thinking about this that you're probably not used to, right? Really thinking about how heavy an object is being a proxy for how resistant it is to being moved, right? And again, we can kind of reverse this operation. So if we say that F of S is equal to ms times the gravitational acceleration, then we can do a little bit of algebra on that, and we see that the acceleration is equal to the force applied to the object divided by its mass. Right? So in the case of the steel ball, you get 19.6 newtons divided by the mass of the thing, 2 kilograms, and what gets spit out is 9.8 meters per second squared. Right? And so the acceleration of the wood would be equal to the force applied to the wood by the earth divided by the wooden ball's mass. And so again, that would be what, 4.9 newtons divided by 0.5 kilograms. And so again, we see 9.8 meters per second squared. Right, so in order for them to have the same acceleration, a different force has to be operating. Okay, and so again, you can see the acceleration is the same. We sort of started from that standpoint, but if you just started by demonstrating experimentally that two things of vastly different mass fall at the same rate, and you could deduce that they have different forces, right? Okay, so that is gravitation. Again, so just an introduction to gravity, concept of gravity. We'll get into more detail later as we proceed through the course. The next force that we want to look at is the force that is very often opposes gravity, and that's called the normal force. So this is the force a surface applies to an object that is pushing against it. This is the force that a surface applies to an object that is pushing against it. Okay, so let's say, the simple, if I have my steel ball here sitting on the table, right, I know that there's a weight associated with the ball, and specifically we've got mg, right? The mass of the thing times g is equal to the weight. And so given that this force is present, why does the ball not just fall? Well, it's sitting on this presumably hard surface, right, like a tabletop, right? And the tabletop actually pushes back on the ball. The ball pushes on the table pushes back on the ball, and so this is what we call the normal force, and we denote it with a capital N. It's again a vector, right? It's again a vector, right? So you got a ball resting on a table. The ball doesn't fall through the table because the table resists it. And this resistance is what we call the normal force. And this is in some ways very patently obvious, but it's also somewhat strange on the surface too if you haven't really thought about it. The resistance that the table has is kind of due to the table's rigidity, right? It's made of matter, and it's got its own internal structure, and it's more or less rigid, right? And so it's going to resist deformation, right? The reason the ball doesn't fall through the table is because it would destroy the table. And so the table has this sort of rigidity, and it resists deformation, and so you get this force in the opposite direction, right? So let's think about this in the context of Newton's second law. So I got the sum of the forces. In this case, that's the normal force plus the weight of the object, the gravitational force, and that's got to equal the mass times the acceleration. Okay, and so let's just assume the ball is sitting on the table and it's not moving, and so it not only has no velocity, it's also assumed no acceleration, right? And so that means this is 0. So that means the normal force plus the object's weight must equal 0. And so the idea here is that the normal force is equal to the weight of the object, but in the opposite direction. Okay, and so this gets us to what the normal force is. The magnitude of the normal force is just equal to the mass of the object times the magnitude of the acceleration due to gravity. Okay, so basically the normal force will match the force that gravity exerts on a body. So it's going to match it. So in the case of our two balls, I got a steel one and a wooden one. They both feel a force, right? The steel ball has a larger gravitational force, 19.6 newtons. The wooden one has 4.9 newtons. And so because the ball isn't accelerating downward, we know that, or upward, we know that the normal force is going to exactly offset it, right? They're going to balance out. And so what that means is that the table will actually vary the normal force depending on what is kind of required in the moment. Okay. So the implication is that the normal force will somehow seemingly know how much force to apply in order to counteract the gravity. So this is, could seem like kind of an occult thing, right? Like, okay, how does it know? I think the best way to think about this is to think of the object's surface as being like an extremely stiff spring, right? It'll actually compress a little bit, right? So the normal force will vary depending on the object, right? But it's not like it's consciously thinking about what object is in contact with me, how much normal force do I need to apply. The best way to think about it is to think of it like an extremely stiff spring. So I would say that's the best way. The best way to think about this is to think of the object of the table top as an extremely stiff spring. So we know how springs work, and in fact, that's one of the forces we'll talk about. But if I can push a spring down, it exhibits it, or it pushes back on me, and the more I push it down, the more it pushes back. So it's the same kind of idea. If I sit something really heavy on a surface, it's going to push down more, so the table's going to push back more. If I set something very light down, it's not going to push down very hard, and consequently the table will not push back very hard either. So that's the normal force. Okay. All right. And let's see. Next up is the friction force. Okay, so let's talk about friction. We're all familiar with friction. This is the force that opposes motion between sliding surfaces. The force that opposes motion between sliding surfaces. Okay, so like the simple example that we would all be kind of familiar with is if I have a heavy block and I drag it across the pavement outside in your front, on your sidewalk in front of your house. It doesn't freely move, does it? It feels like there's something kind of pushing in the opposite direction or somehow holding the block back. That's friction, right? So if I've got a force pushing the block, then there's a force headed in the opposite direction, which we call friction. And there's two kinds of friction. There's what's called static friction. There's also kinetic friction. And we're going to talk about both of those separately, right? Depending on whether the block is moving or the block is sliding, the friction force is actually going to be different. Let's talk first about the idea of the kinetic friction. So kinetic friction, as I said, there's two varieties. Kinetic friction is going to be the type of friction that applies to surfaces that are in motion and sliding. So this applies to surfaces that are in motion and sliding against one another. All right, and so again, let's think about our brick. Flip pages here. Let's think about our heavy brick, right? So what do we got going on with this thing? We got a brick, right, and it's out here. All right, and so I've got some force pushing, we'll say. The other forces involved would be I've got gravity, so mg. I've also just, we just talked about the normal force, which is going to completely offset gravity because it's not falling through the earth, right? It's just sitting there. And then we've got this additional force, which we call the kinetic friction. I'm going to denote that by F with a subscript of K. So imagine this scenario, and this is our brick. Imagine this scenario where the brick is sliding with kind of a constant velocity, right? It's not speeding up, it's not slowing down. Just imagine you could drag it across the sidewalk at a perfectly constant velocity. So if the brick is sliding with constant velocity, right? If it has a constant velocity, it means acceleration is 0, which means we have no net force, right? So whatever the push force is, the kinetic friction force is offsetting it precisely, and the brick is remaining at a constant velocity. Right, so if the brick is sliding with constant velocity, then the magnitude of F push is going to be equal to the magnitude of the kinetic friction, but in opposite directions. Okay, but in opposite directions. Magnitudes will be the same. Now, we also see the normal force and we see gravity in the diagram. It turns out that friction is actually related closely to the normal force. So the kinetic force of friction is actually equal to, and this is, we'll talk about the magnitude, it's equal to the normal force, whatever the magnitude of the normal force, times a constant which we call the coefficient of kinetic friction. So mu sub k is the kinetic friction coefficient. It's a scalar. It's a unitless scalar quantity that depends on the material. Right? So some materials are really slick, some materials are really rough, some resist sliding less, some resist sliding more. So the force of the sliding friction is going to be equal to whatever the normal force of the object is at the moment, multiplied against this kinetic friction coefficient. Right? So if mu sub k is small, then the surface is smooth / slick, right? So if mu sub k is like 0.01, that's like ice. And, it can be even smaller, right? It can be so lubricated and slippery that it's virtually 0. Or I don't believe mu sub k can actually be 0. Friction on the surface is probably not a real thing, but it can be very, very small. It can be, for all intents and purposes, frictionless. And then, of course, if mu sub k is large, then we got a surface that's rough. The surface is rough, like sandpaper, or even sticky. Sticky would have a huge friction coefficient as well. So here we'd be talking about mu sub k approximately 1, or even larger than 1 in the case of something being sticky. Okay. So that's kinetic friction. Now, static friction is real similar. Static friction is real similar, except it applies to... static friction is the type you can be observed when you apply a force and no movement occurs. This type can be observed when you apply a force and no motion occurs. Right, so it's the friction force between bodies that are not sliding. So it occurs between bodies in contact but not sliding. Okay, so the idea here would be if I've got, like, again, going back to my brick on a surface, maybe I pull on the brick. Maybe I pull or push on the brick, I exert a force on the brick, but it doesn't actually move. Right now, you can. This is easy to test, right? Just go get something, stick it on the table, and push on it very slightly. You're applying a force, but the thing's not moving, right? And that's because there is a force counteracting it called the static friction force. Now, static friction force is derived exactly like the kinetic friction force. It's just it's got a different coefficient, right? So the static friction. The magnitude of the static friction force is equal to mu sub s, here where s stands for static, times the normal force, the magnitude of the normal force. Okay, so static friction will resist a push or a pull force up to a certain threshold, right? The static friction will increase until it hits a certain threshold, and finally the object will start moving. Right? And you've certainly experienced this, right? You push on something and it takes a lot of force to get it started, but once it gets started, you don't have to push as hard to keep it moving. And that is the transition from static friction to kinetic friction. In almost all cases, mu sub k is less than or equal to mu sub s. Right? Typically, it's less than. I think maybe it's possible for it to be equal to. But. So the kinetic friction coefficient is almost always smaller than the static friction coefficient. Right, and so just to further illustrate this point, I've got a block sitting on a tabletop, velocity equals 0, despite the fact that I'm applying a force. Right, and that's because in the opposite direction, the static friction force is matching my pushing force, right? And hence no motion, right? Velocity is equal to 0, no motion, because the static friction magnitude is equal to the push magnitude, right? So let's say I push a little harder, right? So maybe I push a little harder, and static friction is going to ramp up too, right? Again, velocity is equal to 0, no motion. Okay, and that's because the force of static friction has grown and it continues to match the force that I apply to the block, right? And hence no motion. So let's say, okay, all right, fine, I'm going to really start pushing, right? So maybe I push really hard. Well, if I push really, really hard, I'm going to meet the threshold whereby static friction gives out. That coefficient establishes a threshold. There's some amount of force that can be applied that is going to eventually break this thing loose, right? And once that happens, the velocity is then greater than 0, right? The object starts sliding. Right, the object starts sliding, and we have motion. And once that occurs, then I still have friction, but my friction is now kinetic friction, right? Which is going to be certainly smaller than the static friction that was required to keep it at rest, right? And so here, the reason the motion starts is because the magnitude of the static friction is less than the force I use to push against the object. And so you push and push and push, the static friction builds up, you hit a threshold, the object starts moving, and then static friction is out of the equation, and you're now talking about kinetic friction. And again, this is something you will clearly notice just when you're out in the world. It's very common to start, if you have to push something, slide something heavy, it'll almost always be the case that you will be able to push on it and detect that once it's moving, it's easier to push. Okay. Right, so kind of to summarize here, we would say that if the magnitude of the push force is less than or equal to the static friction coefficient times the magnitude of the normal force, then that means no motion, right? And as you push and push, the amount of force pushing back, holding it in place, will increase to a threshold. And then as soon as you hit that threshold, so as soon as F push is greater than mu sub s times the normal force, the object will move. Okay, so that's static friction. All right, very good. Very good. A couple more. Right, so we're kind of running around and taking a tour of all the different forces. So the next one up is something called air drag, which we won't talk about a lot, just a little bit. Air drag, or also known as air resistance. Okay, and so this is, we would call this a resistive force. It's a resistive force due to an object moving through and dispersing air. Okay, and we'll be familiar with this. If I drop, an object from the sky, right, it's going to fall, mg, right? And as it falls through the medium called air, right, it's going to have to displace some air. When that occurs, it's like a force in the opposite direction of the object's velocity, and we denote that with an r, and that is the what we call the air drag or air resistance. Okay, and now this can be calculated precisely, and here's what we would say: the magnitude of the drag is equal to 1/2, and then we use a d rho av squared. Now, what are all of these things? D is the drag coefficient. Okay, in a lot of cases, it's approximately 1/2, we'll say. 0.5, we'll put approximately 0.5, 1/2. Now, what is rho? This is the density of the air. Right, so, how thick is the air? If you move up into the atmosphere, the density of the air gets smaller, and so air drag would be naturally less significant if the air is less dense, right? And then A, this is going to be the A, as usual. A stands for area here, so this is the cross-sectional area. It's the cross-sectional area, and specifically that the wind, let's say wind, hits. Right, so it's not surface area necessarily, it's the cross-sectional area. Like in the case of the ball here, the fact that there's a backside to this ball doesn't matter in terms of drag, just the front side here. So it's kind of like this piece here is important in the drag equation. And then V is the velocity, and it's a magnitude, as you can see here. So the speed of the object matters. So the faster you go, the more air drag you get. Okay, and so obviously, we're not going to focus on air drag right now, but you can see that the wind resistance, air drag is a function of, the drag coefficient, the density of the air, the cross-sectional area, i.e. the shape of the object, and how fast it's going. Something that's barely moving has very little drag, but something that's moving 1,000 miles an hour has a lot of drag depending on what it is. Okay. All right, and so that's all we'll say about air drag for now, and we'll jump into the next force, which is the spring force. So this is one we'll use a lot in a lot of our problems will involve springs and dealing with springs. And so this is a force due to compression or extension of a spring. compression or extension of a spring, right? So the way to kind of think about this is, let's draw a little situation here. Say I got some kind of a wall, and attached to it is a spring, right? And now all springs inherent, one of the properties of springs is they're going to have some natural resting position or some kind of a resting length, and we'll denote that resting length as L. Okay, so L is the resting length of the spring. Okay, and so a lot of times what we'll want to do is we'll coordinatize the spring based on its resting length. So we'll set 0 equal to like the end of the spring when it's sitting at its resting length. And so if I push the spring back, let's say I push the spring back to here, okay, right? So my 0 is here. So I've compressed the spring in the negative x direction. Right? When I do that, when I compress the spring in this direction, then the spring wants to push back on me. Right? So if I'm pushing it back to this, if I'm applying a force like this to the spring, then the spring is applying that same force. Sorry, SP we'll say. The spring is applying that same force back at me, right? It wants to get back to its original length. If I push it, try to shrink it down, it doesn't like that. It pushes back, right? And similarly, if I pull the spring, right? If I try to stretch the spring out a bunch, so here's our 0. If I stretch the spring out to here, so a plus x, right? When I do that, I'm applying a pulling force to it, and it applies a pulling force to me. Sorry, FSP. Right, so I pull on the spring, and the spring pulls back on me. Right, it wants to, remember, the thing about springs, they always want to get back to their original length. Right, and if they're too long, they want to shorten up. If they're too short, they want to stretch out. So that's kind of the idea with a spring. We can think of springs as being what's the word? Rest. I can't remember. It resists motion. It's restorative, right? So springs will resist motion outside of L is the kind of the key thing. Springs will resist motion outside of whatever L happens to be. Okay, and Hooke's law is kind of the law that dictates the forces that a spring gives off. And so this is Hooke, a contemporary of Newton's. Hooke's law says F is equal to negative K times whatever X happens to be. And K in this case is the spring constant. So the spring constant here, and really this K you can think of as being a proxy for how stiff is the spring. Okay, the spring constant describes how stiff the spring is. So stiff. So K is the spring constant, which describes how stiff. And by stiff, what do we mean? We mean resistant to stretching and compression. Right, there certainly are. I've seen lots of examples of springs that are so stiff you can't even compress them at all. They're like springs made of steel that have where the spring wire itself is like an inch in diameter, and you're like, you can't even believe that they would move at all, but they do move. It just takes tremendous force to move them, right? So these are like the springs that go into like suspension systems for large vehicles, for example. You can't move them with your bare hands, but they do indeed they do indeed stretch and compress. And so that kind of spring would have a huge spring coefficient, right? It would have a large K. Other kinds of springs that you find, like in the ballpoint pins that you use, are very small spring. You can straighten the spring with relative ease, and so have a very small spring constant. Okay, so then the other thing to note here with the K itself is always greater than 0. K is always greater than 0. The negative sign indicates that the force is always opposite the displacement. Right, so if I've got my 0, okay, if my displacement is here, if it's a negative x, then negative times the negative in the spring constant means that the force is positive, right? And conversely, if my displacement is a positive value, then that tells me that the force is negative, right? So the spring constant always flips the sign appropriately depending on the displacement, which is the x value. How far away from the resting position of the spring have you stretched it or compressed it? Okay. Now, a common scenario here would be like the hanging spring kind of thing. So let's say I've got a spring that's hanging, and maybe at the end of it I've got some kind of a mass. Right, so it's like up on a stand or something like this. So imagine a weight hanging like from a spring. The spring is actually going to stretch out, and it's going to exert a force opposite gravity. So think about like the free body diagram. You would have mg going in this direction, and then because the spring is stretched down, the force is going to be, remember, restorative, right? It wants to get back to its resting position of L. And so it's going to be in the opposite. It's going to be in the opposite direction. Okay. And conversely, I suppose if you were to lift the weight up, then the force would be the reverse. It would want to push the weight down, actually. Okay. All right, and we'll get into lots of examples with springs. So then the last force that we want to talk about here is what's called the tension force. And this one will be very commonly used in our example problems and in things, thought experiments and such. And this is the force that is transmitted through like a rope or a cable. A rope or a cable or like a string. Right, you're going to have some, if you put the string under tension, there's going to be some kind of a force, and it seems to be in the rope. And so the simple example here would be like, I've got some kind of a ceiling, maybe, and then I've got a rope tied to the ceiling. Okay, so I've got this rope, and then at the bottom of the rope, I tie a big rock. Right, so I've got the rock, and I've got a rope. Okay, and so if we suspend the rock from a ceiling like this by a rope, then the rope is going to offset the weight of the rock and keep the rock from falling. It's kind of like the normal force in reverse, right? So here's my free body diagram. I've got mg, and that's being offset by the tension in the rope. Right, the rope is, it's got some solidity. It doesn't want to be stretched apart. It's gonna hold that weight up rather than allow itself to be ripped apart. Right. Okay, and so that's the tension. Tension is actually, you can think of it more as a property of ropes and cables and such. It's not really a force. It's just how it's kind of like the normal force. Normal force is kind of like a table has a certain amount of rigidity to it. Similarly, a rope or a cable has a certain amount of tension that it possesses, right? And it becomes a force when you apply it to something, as in this example, like as you hang something, you put it under some kind of a force, right? So it's really more like a property of a string or a cable, just matter in general, right? Now technically you could create a tension force in anything, really, anything that's, you know, holding up. If you've got, you know, blocks of wood can be put under tension if you're suspending something from blocks of wood. I mean, it technically doesn't have to be a springy rope or anything like that. It's just anything that has tension like that. So a couple things to note about the tension force is that the tension force is always in the direction of the rope. It will always be in the direction of the rope, right? So if the rope is under pressure, it'll straighten out, and the tension is going to be in that direction. You're not going to have tension heading off in some random direction, right? It's going to be in the direction of the rope. So that's the first thing. And the second thing, which is sometimes confusing as you're trying to work out problems, is the tension in a rope is constant throughout the rope. So the tension in the rope is constant throughout, right? It's not like the tension is felt just at the position, just behind the position of the knot or something. It's throughout the rope, right? The whole rope is under tension. At any point on the rope could break due to the tension getting too significant, right? So it's not, there's no, ropes will certainly have weak spots, but they're not weak spots because the tension is different there. Okay. All right. And so the kinds of things we'll be doing with tension, you know, you can imagine, you know, the physics can get kind of interesting when you take something like this. Like, let's say I've got my block here on a surface, you know, and so there's gravity pulling it down, the weight of the block. I've also got the normal force at work here. And let's say I'm pulling on the block, right? So this is just a block. I'm pulling it across the ground, kind of like a wagon, but let's say it has no wheels to make it more interesting. So let's say the rope is attached up here and I'm pulling it at a certain angle. Okay. And so let's throw some friction in here. So maybe we'll just say kinetic friction. Right? The physics in this situation can get really interesting based on the angle at which the tension is applied, because really the tension is going to have two components, like we will frequently see, right? It'll have sort of the x component and the y component, depending on how you coordinatize this thing, right? And so the vertical component, you can imagine, is going to offset the normal force, which will in turn reduce the friction force. So it is possible to set up problems like this to figure out, like, sort of optimally, like, what angle should you pull this block to make it slide, to make the forces kind of minimize, right? And so you can get into some pretty interesting physics problems with tension. But that's basically the tension force. And again, all of these forces, this is just an introduction. A lot of them you're familiar with. Some of them, you know, you've heard of before. It's just going to be, this was just a general introduction. We'll get into all of these in more detail as we start working through problems, and we start to have entire sections dedicated to each of these. So that'll do it for this lecture. The next section, we're going to get into more detail on Newton's first law, and then of course we'll follow up with the second and third. All right, take care.